Hi everyone, welcome back. In today's video, we will continue on the oscillators track. So in the last few videos, we looked at how to design oscillators in Cadence. And we also looked at what the ISF model for phase noise is and what the ISF actually is. So in this video, we'll look at how to simulate the ISF using Cadence. So we'll use the transient analysis tool in Cadence. Okay, so if you remember from the ISF video, the transfer function, the impulse response, h phi of t comma tau is given by the ISF divided by q max times u of t minus tau. Right? You can kind of invert this equation and you can say that gamma is the phase shift, which is given by the time shift divided by the period times 2 pi. So that's the phase shift. And then we multiply with q max and divide with the amount of charge injected by the impulse, right? And q max is the total amount of charge that's being displaced at that node that you're measuring the ISF at. So setting up the simulation is a little bit tricky. It requires some nuance. So we need to be careful about a few things. So we need to make sure that delta Q, the amount of charge injected, is not too small so that you don't end up with numerical errors. It shouldn't be too large as well. Otherwise, you'll get a nonlinear response in this function, which you don't want because the noise signal is small. Then delta should be measured after the amplitude settles down, which means that once you inject the charge, you have to wait until the amplitude variation settles down and you're only left with the phase response, and then you measure the phase. You also need to make sure that the impulse is injected after the oscillator starts up and is settled into a periodic steady state. So we'll see how to do that. You need to make sure the step size is small enough so that you capture the entire ISF with enough resolution. And then the last thing, which I think is the most important, is that the error tolerance should be small in the transient simulation. So you need to make sure that time steps set up in the transient simulation is low. Okay, with that in mind, let's get started with the simulation procedure. So step one is you select the oscillator of choice, and then we need to set the time step. So the default time step is usually set to the transient time divided by 1,000. And in this case, let's say we simulate 100 cycles, which is about 10 nanoseconds at 10 gigahertz. So then the step size would be 10 picoseconds, which is just 1/10 of the period, right? And that's not enough. Typically, I would say you need maybe like T naught divided by 10,000 or T naught divided by 1,000 at least, right, to get something reasonable. So that would correspond to about 100 femtosecond step. But in my opinion, you need maybe 10,000 or even 100,000. So 1 femtosecond or 10 femtoseconds, right? So in this case, we will use 10 femtoseconds just to make it a little bit quicker. But you should verify and check that when you reduce this, the result doesn't change. So we'll do it with 10 femtoseconds, and maybe we'll also verify with one femtosecond at the end, right? So that's because you're trying to capture very small phase shifts or very small time shifts. So you need this step to be at least smaller than the time shift you're trying to measure, right? So we'll set it to about 10 femtoseconds for now. Okay, so let's actually do that. So we'll do step one. So if you go into Cadence, so this is kind of the oscillator that we designed earlier, LC oscillator cross-coupled. And I'll use this model without the current mirrors just for simplicity, right? So it's literally just that. If you don't know what this is, you should go watch that video. Then I'll use ADEL since we used ADL in the past, but Maestro might be better for this simulation. Anyways, so let's load a state. So if you go to oscillators, I think this was 2B maybe, and then say, let's go to the last one. And then we'll load the latest state just to get these parameters in there. Okay, very nice. I don't need any of these. We'll set it up again. So I'll delete all of these. Okay, and we also need to set up an injection current. So I'll copy the impulse current from there, remove these labels, and then we'll connect it up across this transistor. So I'm right now measuring the ISF of this transistor's current source, or this transistor's noise, for example, right? Okay. So I'll say current goes from 0 milliamps to I pulse ISF. And the delay time is, let's say, delay of ISF. Rise time 1 femtosecond, fall time 1 femtosecond, and the pulse width is delta T of ISF. Okay. So that's our pulse that's being injected. We also have a startup pulse out here, and that's the oscillator. Okay. So now I'll say copy from cell view, and what values to set for these, right? So right now I'll just set some values. We'll see how to determine them later. So I'll say, okay, 1 microsecond in amplitude and maybe 1 picosecond in delta T. And the delay we can set to, we'll see how to set this, but for now I'm just setting it to like 10 nanoseconds, just some random values. We'll correct these before we do the simulation. Analysis, I'll say transient analysis, and I'll say I'll simulate this for about 20 nanoseconds. We'll also set this value. And what we care about is this, the time step parameter. So we said this should be 10 femto, right? And the max and min also I'll set to 10 femto and hit OK. You can also play around with other parameters in here, like the conversions, things like that. I'm not doing it with this video because it's probably not required. Okay. Hit OK, hit OK. And that sets that up. Okay, that's good. So we go back in here and we've set up this one, right? So the next thing we need to set up is the impulse location and the maximum amount of time that you want to simulate the transient for, right? So the first thing we'll do is let's simulate this. We need to check it. Okay, check and save and simulate. So this will take a few seconds. So once it's done, okay, so that finished, took a few seconds. Now what I want to do is I want to plot, say, the differential output voltage, because we'll plot the ISF with respect to the differential outputs. Okay, so we see that this oscillator has started up and it's settling down, right? So if you go back to the notes, which is here. So I say, look at the frequency function to find the steady state, right? So we want to find out when this has reached steady state. So one way to do that is to, maybe first I would like to add this to outputs. So I'll say vplot, delete this, close, and then we'll send to calculator. And then let me delete all of this. And then I'll say freak, and then set this to defaults, say okay. And then let's plot this. So if I delete this, so this is the instantaneous frequency, right? And what we want to see is when this instantaneous frequency has kind of settled down. So I'll zoom into this region. And we say, okay, there is an impulse here that should not be there, because right now we want to look at it when that does not have an impulse, right? So let me set this back to 0. That was a mistake. So let me actually rerun this and I'll come back. Okay, after cleaning up removing the impulse, now you can see that there's no impulse in here, of course. And it kind of settles down after a given point. So I like to zoom in here and then see at which point that happens. So if I place a marker, we see that, okay, up until about 5, 6, it's still kind of settling down. And if I just look at the last few digits of this frequency, obviously there's some numerical error in the frequency from the way this computes the instantaneous frequency, but it's somewhat definitely settled at around 10 nanoseconds, right? So that's why I kind of chose 10 nanoseconds. You can be a bit more risky maybe and go down here, but we'll see what happens if you don't let it settle down fully. So let's say it's 10 nanoseconds, right? So we'll choose that value as the delay. So when the impulse kicks in, okay? So that was the first step. And then I said we have to look at the cosine difference spectrum to verify that it is actually in steady state, right? So let's see how to do that. So what does that mean? So for that, I will have to set up a parametric analysis. And then I want to see with the impulse and without the impulse, what happens. So I need to set it to iPulse, and then I'll say 0 versus 1 micro, and then just 2 steps, right? So I'll run the simulation and then we'll see what happens. Okay, so the simulation finished. What I would like to do is plot it. I guess it should actually pop up a plot once it's done. And we have these 2 results. So I'll send these 2 to calculator. And then I want to subtract them. Since it's already in the buffer, I can just hit subtract and we'll plot that. Let me delete this. Okay, so what do we have here? So once the impulse hits, we see that the difference between when the impulse was there and when the impulse was not there is again another sinusoid, right? Now, why is that, right? If you go back and look at these equations, if I have, let's say, cosine x and a shifted cosine, you take the difference between them, you get cos x minus cos x cos phi minus sin x sin phi. And since phi is very small, the shift is very small, this is basically just cosine x, and this cancels that, and we end up with minus sin x sin phi. And sin phi can be approximated as phi for small arguments, so it's just essentially minus of phi sin x, right? So you do get a sinusoid at the end. If this is a fixed phase shift, then you should get a sinusoid where the amplitude of that sinusoid is equal to that phase shift, right? So this is one way to verify that you are indeed getting a fixed phase shift that is settled. So we can see how long it takes to settle. And to do that, I can send this to the calculator and once again apply the freq function, right? So I'll say freq and then hit OK, and then we plot that. Okay, so let's delete this. And we see that, okay, it's DC in the beginning, and then eventually it starts to settle down. So this tells us when the phase actually settles down, right? So if we look at this and I place a marker, and we see that the impulse came in at around 10, and by about, definitely by 11, it's sort of settled, right? So zoom in here. Not by 11, sorry, by about 15, I would say it's kind of settled. Okay, so what this means is that we only need to simulate up to 16 nanoseconds because we can measure our impulse response at 15 nanoseconds or so. So that gives us another part of the puzzle is when to measure, right? So I can change this now to 16 nanoseconds, which makes things a bit faster. And I can change the delay of when to measure. No, that's not where we're measuring. So that's fine. That's when the pulse hits, right? So once the simulation is done, we still need to know what this needs to be, right? The delta T ISF and what the I pulse value needs to be. But at least we know when to start the delay and then when to collect the impulse response. So we saw actually that it looked like as if it had settled even at 8 nanoseconds. But what happens if I actually set this lower? So if I set this to 8 nanoseconds, I would like to know what that does to the output, right? So let's simulate this and look at the result again. Okay, that simulation is done. We'll repeat the same procedure. Say send to calculator, send this to calculator, and then we subtract them and we want to plot the cosine difference. Let's take a look at that. Okay, so you see actually that the phase shift is not steady, right? Which means that the oscillator had not settled before we put in the pulse. So you need to make sure that that's the case. Right, so make sure you plot the cosine difference and then see a nice sinusoidal signal. And you can actually also look at the spectrum of that sinusoid and make sure there is a single frequency at 10 gigahertz. So let's go back and do that quickly. So I'll rerun the simulation at 10 nanoseconds, and we'll look at the spectrum. Okay. Okay, so that got done. Let's send this to calculator and then do the cosine difference again. Okay, so that's good. So what I want to do is to plot the spectrum of this. And I don't want the signal up to maybe 11 nanoseconds or maybe even 12 nanoseconds. Right, so from 12 to 16 is only what I want to look at. If I plot the spectrum, so make this bigger. So you see that there's a nice single frequency at around 10 gigahertz, right? Which is good. That's exactly what you want. And this curve kind of comes from the fact that it's windowed, right? Okay. There's also harmonic content. I'm going to ignore that for now. And you can actually kind of see that it's only the odd harmonics, right? We'll get to that later when we look at the ISF. Okay. I kind of alluded to that earlier. Since we're looking at a differential signal, it should not have any even harmonics, but anyways, let's go back. So we have this now, so we know when we are starting, when we are stopping. We need to figure out other parameters. So the next thing to look at is, yeah, we need to find the zero crossing or when the impulse is off, right? So that's what gives us the delta t, right? So let's do that. So I'll close this, don't need this anymore. We'll set this to 0, that's right. And then I'll run a transient simulation again. So essentially we need to find a reference pulse, so a reference signal from which the phase shift is measured, and that's what I'm doing here. Okay, simulation completed. We'll send this to, sorry, I want to send this to the calculator again and delete these. And I'll use the cross function to find when this output crosses 0, right? So that's 0, and I want to find edge number, let's say 200 for now, or let's say 300, and I'll hit OK. And I see that it crosses 300 around 14.88, right, which is close. I would like it maybe beyond 15, since we said, okay, at 15 is when the pulse comes in at 10, and then at 15 is when we saw that we wanted to measure beyond 15, right? So I'll set this to maybe 320. That's 15.87, so that's pretty good. So that's very close to the end, right? We don't want to be too close to the end, so maybe I'll reduce it a little bit. About 315 sounds good. Okay, so that's very nice. So we'll use 315 for now. And if I actually evaluate this number, it gives me 15.62. But I want more significant digits, right? And what you can do for that is you go options, significant digits. Let's say I take about 12 significant digits. Now I'll recalculate this and it gives me 15.62237, whatever, right? Now the difficulty is when you send this expression, if I want to send this expression and save it, we need to change from 0, we need to change this to 1 micro and then sweep delta t, right? Or delay, we need to sweep the delay. So it becomes a little bit tricky. So instead what I would do is just save this numeric value. So I'll say Control C, and I will actually set, let me send this to expression, save the numeric value and subtract it from the measured value, right? So essentially when you do this now, you should get 0, right? So let's see what happens. I'll send this to ADE, close this, and then I'll run this again. And we should ideally get 0, right? Because we're subtracting the number from itself. Okay, simulation finished. But what happens when we look here, it's not 0, it's 2.8 femtoseconds, which is quite a lot, right? And the reason behind that is that when you click into this, you'll see that actually ADE truncated this value, and it's not exactly the value that we calculated earlier. So there is no, as far as I know, there's no way to kind of directly fix the significant digits in ADE. We should actually move on to ADE to Maestro, which we'll do in the next couple of videos probably. But since we are working in ADE, I found a workaround. And the way you can kind of do this is you print this whole value in here, and then we will actually separate this into 2 different units. So let's say I pick this point and then say this is nano minus 0. Actually, we'll cut it off once here. So minus 15.622 nano minus 0. Pico. And then we'll make this femto, right? So I've essentially just kind of like divided it up, the original value. What was the original value? The original value was, even here it doesn't show up. Okay, anyways. So the original value, I believe, was, we can print it here, 622.377.1172. So 622 is in nano, 377 in pico, and 1172 in femto, right? So that's kind of the workaround that work. So let's use this expression and then say, okay, and I'll run this again, and then we'll see what the result looks like. Okay, I had a small kind of bug, which is that you need to make sure there is a space between the negative and the value for all of these values. But if you do that and then hit OK, then you see that now this is like the error is on the order of 24, 10 to the minus 21, right? Which is much smaller than a femto, which is good because essentially in this we had down to around 10 to the minus 19 or so, right? The values was up to 10 to the minus 19. So error is much less than that. Okay, that makes sense. You don't really need to go below that, I think, because there's already numerical error that shows up at that point. So since we set the time step only to 10 femto, I don't think you can do much better than that. And that's why this kind of transient simulation approach is very slow. So ideally, you would want it to be even less than that. Okay, anyways, now what we can do is we can, if we go back here, that's kind of what I've written out here, is you subtract it and then you check that it's 0 before running any sweeps. So the next thing we need to do is test the linear response range to find the value of these two, the I pulse and the delta t. Of course, delta t I've set here to be 1 pico, which is about 1/10 of the time period of the wave. You can also reduce this a little bit if you like, but 1/10 is 100, sorry, since the period is 100 picoseconds. I've set this to be 1 picosecond. That's a good number, I think, around 1/100th of the time period. And the impulse value is what we need to find. So to find this, what I will do is let me actually call this the time shift. Okay. We'll run one more parametric sweep. So sorry, now I need to set this to 1 micro. Oh no, this is 2 0. So first I need to sweep I pulse ISF, say from 0 to 1 milliamp. Right? That's a lot actually. And I'll say maybe 11 steps. You can make this auto, that's fine. You can also make it logarithmic, but it's better to be linear because we want to see a straight line. Okay, so let me run this and see what happens. This will take some time because each one is a bit slow. Okay, so that simulation finished, and you can see that it's very linear, even up to 1 milliamp, which is a lot, but we probably won't use it all the way up to 1 milliamp. We can set it down to like maybe 10 microamps or so. All right, so that's good. We know now how much to set this to. So I'll set this to maybe 10 microamps. And we know how to set the delay. We know how to set the time period, basically these two values. I guess we haven't really looked into that. So we know that the Q max is VP peak, the differential V peak, because we're measuring differential signals at the output times C out, which is, we saw in the previous video that this value is around VTH, which is 580 millivolts, and C out is a series combination of two capacitors, which are each 290 femtofarad, which we calculated. That was the output capacitance. So which means that the total swing is around 84 femtocoulomb, which is approximately 10 to the minus 13 coulombs, right? And we want to make sure that the amount of charge injected into it is less than Q max by a factor of 100, so 10 to the minus 15 coulomb, right? And the charge injected is I pulse times delta T pulse. If I set this to 1 pico, which is 10 to the minus 12, we need to make sure that this is around at most 1 milliamp, right? And that's what we saw, that we went up to 1 milliamp. But I want to go below this. Let's say 10 microamps or 100 microamps is also fine, right? Okay, so let's set it to maybe 10 microamps, and then see what happens. So I'll simulate this, and we want to look at what the time shift is. Okay, so we see the time shift is estimated to be around 1.36 femto. This is a little bit small actually, because initially we set this to be about 10 femto in step. So what I would like to do is maybe make this 200 micro. Okay, and then we'll resimulate this. So this should become 20 times that, right? So 1.3 times 20 is around 1.36 times 20 should be around 27.2 or so. So let's see what we get. Okay, as expected, we get 27.1 or so. So I guess 200 micro is a good number. If you want to be conservative, maybe, okay, we can go to 100 micro. And then now we're ready to basically simulate the ISF, which is the last step, right? We just need to sweep the impulse over one period, and then we'll get the ISF. Okay, so let's do that. Actually, we get the time shift, and from that we can calculate the ISF. So what I'll do is I'll say, okay, iPulse. We don't need iPulse anymore. Actually, we need now we need to sweep delay of the ISF from 10 nano to 10.1 nano, because 0.1 nano is the time period. And the number of steps, I'll just set it to 21 for now, but you may want to increase this to get somewhat better results. It doesn't change the shape really. It just gives you more samples essentially, right? So let me simulate this. This will take a few minutes. Once it's done, we'll come back and take a look. Okay, so finally it's done, and you can kind of see what that looks like. And this looks good, but right now this is not yet the ISF. We need to kind of scale this. So I'll say send the expression editor, but I don't want to use this whole thing. So I'll just say, actually, yeah, okay, that's good. So let's go back and shift, plots correctly. Okay, so now we need to scale it by a few factors. Let's go back in here and look at them. So this is the delta t value, and we need to add in all these factors, right? So let me do that. So I'll say time shift divided by 0.1 nano, which was the time period. And this whole thing times 2 pi times Q max, which is we calculated that to be 84 femto coulomb. So I'll say 84.1 femto. And that is divided by delta Q, which we can write in terms of variables. I called it iPulse ISF and del T ISF, right? iPulse ISF. Some brackets times del T ISF. Okay. That's pretty much it. Plot this, see what we get. Okay, so we get some result here. So we see that the ISF is in milli. It's unitless, I guess. Milli radians in this case, which makes sense. Okay, so one last thing I want to look at is ISF versus the voltage waveform, right? So that'll give us some idea. So I've sent this to, you can click on this and send it to the outputs, and then I'll rename this to ISF. Okay, and we can close this for now. And before looking at the voltage waveform, I wanted to check one thing, which is that if I reduce the transient step to 1 femtosecond, how does that change the result? So I actually went ahead and ran this overnight just to compare them. And you can kind of see the comparison result here. So it's very similar. So the value that we chose of 10 femtosecond should be good enough. the shape is basically identical, right? Of course, since we calculated the center value or the normalization value in this expression, which is, sorry, in the time shift expression, we calculated this value using 10 femtoseconds. That's why it's offset. If you calculate even this value using 1 femtosecond, they should be identical. Okay, so it looks like this is the actual ISF. So let's look at the voltage waveform just to be sure that it makes somewhat sense. So what I can do is I'll plot this, let's say new window, and then plot this. And it's going to plot many results, of course, because I calculated it for many of them. I'll just send one of them to the calculator and we will clip this. So actually it's already set up, but let me just do it again. So I'll say clip, and I want to clip it from 10 to 10.1 nanoseconds. Although we measured the phase shift much later at around 16, 15, 16 nanoseconds, the phase shift was introduced by the impulse in this band, in this range, right? That's why we want to calculate the voltage and compare it with it in this range. So I'll say, okay, and then plot this. And I think it's going to plot it for all of them again, or maybe not. Okay, there we go. So that's what that looks like. And if you compare it, let's compare it with ISF. That we got. Okay, so if you compare it with the ISF, then we can see that when the voltage is 0, so let me place a H marker here, around there, 10.01 and 10.06. If we look at 10.01, it's maybe somewhere here, and 10.06 is close to the peak, right? So we see that, okay, when the voltage is close to 0, we have the peaks in the ISF, right? Which kind of makes sense. And if you look at the peaks, so the peak of the voltage is occurring at that value. And if you place a marker here, say 10.03 and 10.08 or so, so which is 10.08 and close to 10.03. So we see that the 0 value for the ISF is close to the peak values of the voltage. So it kind of makes sense that this is what you expect from the ISF model. So that's it. So that's how you extract the ISF. I mean, this is a very slow approach, of course, because it's transient simulation. It takes a long time. And future videos, we will have to look at how to generate the ISF using periodic transfer function, PXF simulation. But to do that, we first need to introduce the PPV model, which will take some time because that's a little bit more technical. So we'll develop the PPV theory. Actually, before that, I will show you how to simulate cyclostationary noise sources, so the noise modulation function. And then once we do that, that will complete the ISF simulation part. Then we'll move on to PPV analysis, PPV model, and then show how to simulate the PPV, which is actually much easier, much faster. And we can use the PPV model also to get a lot of insight into the oscillator, but it can also be used to regenerate the ISF model backwards using the PPV. So we look at all that, and that should complete sort of this oscillator track, at least at RFIC. We'll use all these concepts to then move to millimeter wave. Okay, hopefully you're excited about that. And hopefully this was a useful video. If I made any mistakes, or if you have some suggestions on how I can improve these simulation results, you can please leave them in the comments. So that'll be very helpful to everyone. Thank you. Have a nice day.